Hi, I'm Ms. Hearn. Let's get started. In this video, which is for our business calculus class, we're going to look at the product rule and the quotient rule and how to apply them to taking derivatives of functions. So a product rule refers to the fact that if we have the derivative of a product, we can't just take the derivative of each part. So what I mean by that is if we had the function y equals, say, x cubed times x squared, you might think that you could say that y prime is 3x squared times 2x, which is equal to 6x squared, x cubed rather. But that's not actually true, because if you think about it, x cubed times x squared is x to the fifth, and the derivative of x to the fifth is actually 5x to the fourth. So that would be completely different. So we would have been absolutely incorrect to take the derivative of each part of the product. However, there is a way that we can take derivatives of products of functions. And the way that it works is if you have a function y equal to the first part of the function times the second, so we'll call those f times s, where f and s themselves are functions, then we can take the derivative by finding the first function times the derivative of the second plus the second function times the derivative of the first. And similarly, when you're taking the derivative of a quotient, you have to use something called the quotient rule. If you have a function y that's equal to a top function t divided by a bottom function b, you can't just say, okay, it's the derivative of t divided by the derivative of b. But what you can do is you can take the bottom function times the derivative of the top minus the top function times the derivative of the bottom and divide that whole thing by the bottom function squared. So we're going to practice using these two rules. Here's some examples. All right, so first we're going to use the product rule to find the derivative of 2x squared times the quantity 3x to the fourth minus 5. Now previously, by the way, we knew how to find this derivative, but we used some algebra to do it. What we did is we distributed this first. 2x squared times 3x to the fourth is actually 6x to the sixth, and then we distributed the 2x squared to the negative 5 and got negative 10x squared. And then we said, okay, f prime of x is going to be, let's see, 6 times, by the power rule, derivative of x to the sixth is 6x to the fifth, minus 10 times, that would be derivative of x squared is 2x. So we would conclude that f prime of x is actually 36x to the fifth minus 20x. Okay, so one method is to rewrite the function before you actually differentiate. But we're going to instead use the product rule. And so to do that, we have to identify what is the first part of the function that's being multiplied times the second part. So the first part of the function we'll call capital F for first, and that's 2x squared. And the second part would be 3x to the fourth minus 5. First function times second. So we're going to follow the pattern. F prime of x, that's little f prime, is going to be the first times the derivative of the second plus the second times the derivative of the first. So off to the side here, I'm going to write down what my derivative of the first is. So the derivative of 2x squared is 4x. And the derivative of the second function, 3x to the fourth minus 5, that's going to be 3 times 4x cubed minus 0, or in other words, that's 12x cubed. So now we have what we need to plug into our product rule formula. The first function, which is 2x squared, times the derivative of the second, which we found to be 12x cubed, plus the second function, which is 3x to the fourth minus 5, times the derivative of the first, which we found to be 4x. And now we just have a little simplifying to do. So we have 2x squared times 12x cubed is 24x to the 5th, plus, distributing through the parentheses, 4x times 3x to the 4th is going to be 12x to the 5th, minus 5 times 4x is 20x. Now combining these two like terms, we get 36x to the 5th minus 20x. Now you might say, Miss Hearn, it's a lot easier to do it the other way where you rewrite the function first, and I'd absolutely agree with you. But right now we're just practicing using the product rule because there are lots of functions for which we have no choice, and this is another tool in our tool bag. Okay, so let's now find the product rule for this next function. F of x equals 3x minus 4 times 2x squared minus 3x plus 1. So to use the product rule, we have to identify the product. So the first part of the product, capital F, is 3x minus 4. The second part of the product is 2x squared minus 3x plus 1. We'll call that S. We know we're going to need f prime and s prime. So the derivative of f is just 3. And the derivative of s, so let's see, derivative of 2x squared is 4x, derivative of negative 3x is negative 3, derivative of 1 is 0. So the derivative of the second function is 4x minus 3. Now we're going to write down our rule, our product rule. So the derivative of little f is going to be first function times the derivative of the second, plus the second function times the derivative of the first. Now we just fill in each of those functions. So capital F, 3x minus 4, derivative of s, 4x minus 3, plus s is 2x squared minus 3x plus 1 times the derivative of the first, which is 3. Now we have a little bit of distributing to do. So f prime of x is equal to, here we're going to FOIL. So 3x times 4x is 12x squared. 3x times negative 3 is negative 9x. Negative 4 times negative 4x is negative 16x. Negative 4 times negative 3 is positive 12. And over here we're just going to distribute the 3. So we have 6x squared minus 9x plus 3. And let's see what we get here. We're going to combine some like terms. 12x squared and 6x squared. So f prime of x equals 18x squared. We have negative 9x, negative 16x, and negative 9x. So that's going to be negative 34x altogether. And plus 12 and plus 3 is plus 15. All right. Now we're going to use the product rule for some functions where simplifying algebraically is not an option. And in order to work these problems, we need to recall a couple of derivative rules that you may have forgotten. So let's write them up top here. So the derivative of the function e to the x, if you recall, is just e to the x. E to the x is an interesting function because the value of the function at any point is also the value of its slope at that point. All right, and then the derivative of the natural log of x is actually just 1 over x. So keep those in mind as we work these two problems. So we're finding the derivative, and notice it doesn't tell you to use the product rule, so there's no hints here. So you just have to know that when you have something with an x times something with an x, that you have a product of two functions and that you have no choice but to either simplify or use the product rule. In this case, you cannot simplify, so you have to use the product rule. So we're going to write down the derivative of the first. So 2x cubed has the derivative 6x squared. And the derivative of the second is the derivative of e to the x, which is just e to the x. And then we're going to write down our formula for the product rule. First function times the derivative of the second plus the second times the derivative of the first. And then we're just going to fill in each part. So f prime of x is going to be the first function, which was 2x cubed, times the derivative of the second, which was e to the x, plus a second function, which is e to the x, times the derivative of the first, which is 6x squared. But we're not done yet. That is the derivative, but it's not in the form we usually leave it in. Usually with these problems, it's very helpful to factor. And one of the reasons is because we're going to eventually get to the point where we're taking the second derivative, the derivative of the derivative, and we would like it to be in factored form. To do that, it's also helpful for other reasons like finding where the slope of the tangent line is 0 and that sort of thing. So in lots of cases, this is not the ideal form for the function to be in. So what we're going to do is just factor out the GCF of these two terms. You can see that both terms have in common a 2 and an x squared and an e to the x. So let's see what's left behind in this first term, 2x cubed e to the x. Well, that's just an x left behind. There's nothing else there. Plus, in the second term, let's see, we took out the e to the x and the x squared, and from the 6 we factored out a 2, so there's just a 3 left behind. So generally, this is the format that we like to leave our derivative in, factored. Okay, let's try part B. So again, we have something with an x, so we'll call that our first function, times something with an x, that'll be our second. So our derivative of 6x to the fourth, bringing the 4 out front, we get 24x to the 1 less than 4, which is 3. And then the derivative of the second function, natural log of x, is just 1 over x. So now we write down our formula for the product rule. First times the derivative of the second plus second times the derivative of the first, and just fill in that pattern. So f prime of x is equal to 6x to the fourth, the first function, times the derivative of the second, which was 1 over x, plus the second function, which is natural log of x, times the derivative of the first, which was 24x cubed. In this first term, we can cancel x with one of these in the x to the fourth, and we get 6x cubed, plus usually we write the polynomial in front of the natural log so we don't confuse it as being in the argument of the natural log. Only the x is in the argument of the natural log. And then similarly to before, if you can factor, we would do that. We can factor out a 6x cubed, leaving behind 1 plus 4 natural log of x. So there's our derivative in its simplified form. Okay, so those were quite a few product rule examples. Let's look at a couple of quotient rule examples. I'm going to remind you what the quotient rule says. The quotient rule says that if you have y equal to a top function over a bottom function, then y prime is going to be bottom d top minus top d bottom over the bottom squared. So once again, you're going to need to know the derivative of each part of the function. So in this case, we have f of x equals x squared over 2x minus 1. So we're going to think of the top part of the function being the x squared, the bottom part being 2x minus 1. So the derivative of the top would be 2x, and the derivative of the bottom would be just 2. Now we're going to fill in our pattern. So if f prime of x is bottom d top minus top d bottom over bottom squared, then that means that f prime of x is going to be 2x minus 1 for the bottom function times the derivative of the top, which is 2x, minus the top function, which was x squared, times the derivative of the bottom, which is 2, divided by the bottom, which is 2x minus 1, squared. Now we have a little simplifying to do. Once again, factoring is ideal whenever possible. So even though in this case distributing and then combining like terms would be equally easy, it's not always the case. So I just want you to get in the habit when you're doing product and quotient rules of factoring whenever possible. So for example, in this case, notice that we have a 2 in common here. And we also have an x that we can take out of each of the terms. One of these x's on the second term can come out. So I am going to factor out 2 and an x, and we'll see what's left behind here. So in this first product term, we left behind the 2x minus 1. We took out the 2x. And then minus, in this second piece, we took out a 2 and one of the x's, so there's an x left behind. And then in the denominator, we have 2x minus 1 squared. And now we should really simplify a bit more. So f prime of x is equal to 2x times 2x minus x is just x minus 1 over 2x minus 1 squared. Now there's nothing that can reduce here, so we're done. Okay, let's try another one. We have y equals a squared minus a over a cubed plus 1. Find y prime. Okay, so we see that we have something with a variable over something with a variable. That means we're going to use the quotient rule. So we're going to identify our top function, which in this case is going to be a squared minus a. Our bottom function is a cubed plus 1. So the derivative of the top is 2a minus 1, and the derivative of the bottom is 3a squared. Now we're going to write down the pattern. So we know that y prime is going to be bottom d top minus top d bottom. That's my short way of saying derivative of the bottom over the bottom squared. So plugging in what we know each of those is equal to, the bottom was a cubed plus 1. The derivative of the top was 2a minus 1 minus the top, which is a squared minus a, times the derivative of the bottom, which is 3a squared, all over the bottom squared, a cubed plus 1 squared. Okay, now what we would like to do is to factor if possible. So looking at this numerator and thinking about if we could factor, if you look at the first term, a cubed plus 1 times 2a minus 1 doesn't have anything in common with a squared minus a times 3a squared. And even if we factor out a cubed plus 1 into a plus 1 times a squared minus a plus 1, and we factor out a squared minus a into a times a minus 1, we still don't have any factors that are in common. So we have no choice this time but to just multiply everything out. So we're going to multiply a cubed plus 1 times 2a minus 1 by just foiling. So a cubed times 2a is 2a to the 4th, plus 1 times 2a is 2a, minus a cubed times negative 1 is a cubed, plus 1 times negative 1 is negative 1. And then I'm also going to distribute here, so we're going to have minus 3a squared. When this negative gets distributed to each term, be careful with the signs. It's going to be, I'm sorry, not minus 3a squared, minus 3a to the 4th, and a plus 3a cubed. And so we can combine like terms next. So this is going to be y prime equals 2a to the 4th minus 3a to the 4th is negative a to the 4th. Negative a cubed and positive 3a cubed is positive 2a cubed. And then we have plus 2a, and then we have minus 1. And this is all over a cubed plus 1 squared. Here's another quotient rule example. We have the natural log of x over 2x plus 5. So our top function is the natural log of x, and our bottom function is 2x plus 5. And so the derivative of the top is 1 over x, and the derivative of the bottom is 2. So we're going to fill that in. So f prime of x is going to be bottom d top minus top d bottom over the bottom squared. So that means f prime of x is going to be 2x plus 5 times 1 over x minus the natural log of x times 2 divided by the bottom squared, which is 2x plus 5 squared. All right, now in this case, again, we have our derivative, but we never leave a function in a form where we have a complex fraction, a fraction within a fraction. The first thing I'm going to try to do, though, is look to see if I can factor anything out of these two terms. And I can't. There's nothing in common there. So I'm going to multiply the top and the bottom of this fraction by the denominator of that little fraction, x. So really, by multiplying by x over x, I'm really just multiplying by 1, so I'm not changing the value of the function. I'm going to distribute the x in the top to the first term and to the second, and the x in the bottom to this term on the bottom. So we have f prime of x equals 2x plus 5 times 1 over x times that x minus the natural log of x times 2 times x over 2x plus 5 squared times x, although I'm going to write the x in the front there. That means f prime of x equals, this x times 1 over x is x over x, or just 1. So that gives us 2x plus 5 minus 2x natural log of x over x times 2x plus 5 quantity squared. And there's really nothing else you can do with this. This term, and this term, they're not like terms. And we can't combine them, and we can't factor anything out that's in common either. So this is going to be our best possible form for our derivative. So let's look at, before we quit today, let's look at this one example of an application using the rules that we've learned today. The total sales S of video games in thousands of games T months after the game is introduced are given by S of T equals 125 T squared over T squared plus 100. Part A of this problem asks us just to find S prime of T. So looking at the function, we have to realize that when we have something with a variable divided by something with a variable, that's going to be a quotient rule problem. And for the quotient rule, we break the function down into the top part and the bottom part. In this case, the top part, the numerator, is 125 t squared, and the bottom, the denominator, is t squared plus 100. So let's take the derivative of each part. T prime is going to be 250t, and b prime is going to be 2t. Now we're going to write down our pattern. S prime of t equals bottom d top minus top d bottom over the bottom squared, and you do need to memorize that. And we're going to fill in each piece. So S prime of t is equal to t squared plus 100 times 250t minus t, which is 125t squared, times b prime, bottom's derivative, which is 2 times little t, all over the bottom squared, so t squared plus 100 squared. Next, we're going to factor whatever we can out of the numerator. I see that these two big terms here have at least a 2t in common. So I'm going to factor out 2t, and let's see what's left behind. In the first term, we have t squared plus 100, and I divided out the 2t, so that leaves 125 instead of 250t. Minus, I took out the 2t there, so that's 125t squared. Oh, look, I missed something. There was also a 125 we could factor out. So let's factor that out too instead. So really I'm factoring out 250 from each term. So that's going to be 250t, and let's see what's left behind. So we have t squared plus 100 minus, we took out the 2, the 125, that's our 250, and one of the t's, so we're just left with t squared, all over t squared plus 100 quantity squared. All right, so this is our derivative written in a slightly different way. And now I'm going to simplify. I have t squared minus t squared. That's going to cancel. So that's going to leave us with 100. 100 times 250 is 25,000 t over t squared plus 100 squared. So this is the derivative of the sales function. And now it asks us to find s of 10 and s prime of 10 and interpret them. So plugging into each of these functions, for s of 10, we get 62.5. But remember, that's measured in thousands of video games. So multiplying by 1,000, that's 62,500 video games sold. Those are the total sales at 10 months. S prime of 10 is 6.25. But that again is in thousands. So multiplying by 1,000, that's 6,250. Now this is a rate of change in sales per unit of time, which is per month. So this is a good sign that the total sales are increasing by 6,250 per month. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That will help other students to find the video.